All right, now for a couple problems where it'll make us think a little more. So let's take a look at this first one. You have an investment that grows from 5,000 to 7,000 in 4 years, continuous compounding. Find the annual interest rate, and then find the amount after 6 years. Two different questions there. Okay, so my answer, I always want to find the function for any of these problems where you have to find the rate first. So my answer will be, so look at my formula, I got this initial amount, e to the RT. So how do I have a function? I need to put the parameters. I need the initial amount and I need the rate. And then I can answer this question. This question will be easy once I find that. The tricky part is finding the interest rate. Okay, so this is given. The initial amount's 5,000, so that's good. And then this is the variable, input variable, output variable. E is a constant, so the only thing I don't have is this parameter R, and I have enough information to find it. Okay, so I can also do like my little chart if I want. Input, output, 0, output 5,000, input 4, output 7,000. That might help me because I'm going to need this other point. The other point's not just there, it's there for a reason. It's going to allow us to solve for R. Okay, so plug in what I know so far. I know that the initial amount's 5,000, that's given. And then plug in the second point. So I plug in 7,000 is the output, and the input is 4. Okay, and that should look familiar. That's an exponential equation. I can solve that by first dividing by 5,000. We've solved a bunch of these by now. So I get 7/5, if I reduce that, equals e to the 4r, natural log both sides. 4r equals the natural log of 7/5. And then I can find r by dividing. Okay, so r will be the natural log of 7/5 divided by 4, which when I plug into my calculator, I get approximately 0.084. Okay, so now I have a function, a complete function. It's 5,000 times e to the RT, and I can answer any question that you got for me. And the question is, how much after 6 years? So that would just be input 6. I run that through my calculator, and I get approximately $8,276. So that's the answer to my second question. This was the answer to my first. And then I kind of asked myself, does that make sense? Well, in 4 years, it grew $2,000, and it's continuously compounded. So 2 more years, I mean, it's not linear, so you can't check it just by, it's not going up by the same amount, right? It's an exponential growth, but it kind of makes sense, right? In 2 more years, you're up to here. So I mean, it should definitely be more than that, and it seems about right. Okay, let's take a look at the next one. Substance decays to 25% of its original amount in 10 years. Find its exponential decay model. Okay, exponential decay looks just like our money one. I'll use A for this one. The total amount is some initial amount, E, and then it's decaying, so we typically use a K instead of an R, and it should be negative, right? Because they have a decreasing exponential function. If you graph it, it looks like that, and of course, our model would really just start here, so this stuff wouldn't make any sense. And then it just decays as time goes on, decreases in an exponential fashion. All right, so let's see, this is what I know so far. So here's what's different. This is the same idea as this first problem, only we were given some solid values, right? We were given this. So I could kind of do the same thing here. So let's try it. Input, output's A. So when time is 0, I have my initial amount. Similar to when time was 0, they gave me the initial amount of money, 5,000. And then in 10 years, write an expression. In other words, I don't really need an initial amount if they're giving me a percentage of the initial amount. So it's 25% of the initial amount. So that's, if this were 1,000, this would be 250. So we're 2,000, this would be 500, right? Or initial amount and then just take a quarter of it. All right, so it works the same way. Does that work? Well, let's find out. So I'm going to treat it the same. I need to know K. So can I solve K this way? Well, let's see. The initial amount I'm calling A naught, and then I'm going to plug, so I go right to the step where I plug in the second point. So it's 25% of the initial amount equals the initial amount, and this is a little sub-zero. We use this in math. We call that A naught. That means kind of the what you're starting with. In this case, the initial amount of whatever this thing is measured in. And then it's e to the negative kt, but t is 10 when you're down to 25%, so I'll put a 10 in there for t. And then you say, well, how am I going to solve this for k? I got too many letters in there, too many variables. Well, here's the good news. Step 1, divide by this number, just like we did here. Same step. All right, and that goes away. Like, you're just left with the 0.25. If this were increasing and you say it doubles, like let's say your money doubles, in this case it was 10,000. You divide both sides by 5,000 and you get a 2 over here instead of a 7/5. Well, if it's 25%, you divide both sides by the initial amount, and you're just left with the 0.25. Works the same way. So now I have 0.25 equal to e to the negative 10k. And now this should look familiar. Take the natural log of both sides. The right cancels out. Natural log of 0.25. And then I divide by negative 10. The negative's important here. I understand my model's decreasing, so I have to include the negative. As you work with logs, you'll realize that when you take the log of a number less than 1, you get a negative. Real quick explanation if you know your log. We didn't spend a lot of time with the log function, but when x is greater than 1, the natural log function is positive. And in this little space here between 0 and 1, everything's negative. Okay, so this will give me the way it's set up is a positive k. Natural log 0.25 negative number divided by a negative number gives you a positive. And that's right because we set it up as k being positive, but the overall exponent negative. And when I plug that into my calculator, I get 0.14. So that's my decay rate. Exponential decay model. So now my model is complete. I'll just save myself a little time and I'll plug in my k up here, 0.14 t. And that's my model. Now I don't have a value here. Like we found the model in the last one with the money problem. That was here. If I said find the model, this would be the answer because we knew the initial amount was 5,000. This one we know a little bit less information. We don't know what the initial amount is, so we just have a name for it, A naught. Otherwise it works the same, and now we don't have to answer any other questions. This next one will be a little more complicated. It's my last example. So let's see. Same idea here. So somehow you know it's 65% of its original amount and you have the half-life. So I would say, okay, I have a function, we'll call it A. I have initial amount, same idea. Let's see. Down here in my notes I call it N. Doesn't matter. All right. So we need to find, well, we need to find K, and then it's going to ask for the age. So this one's a little trickier. So if I did my little chart, I say, okay, T output 0, it's A naught. It was found to have 65% of A naught, but I'm not sure what the input is. That's what they're not really sure about that one. But we do know this, that if the half-life, let's translate the half-life to like what we did in the question above. We were given that a quarter of it was left after 10 years. So the half-life would mean if the half-life is that many years, so that means half of the initial amount is left after this many years. Okay, same idea as this one. It's just kind of given indirectly. Half-life, half the initial amount, takes that long for it to decay in half. Okay, good. So this should allow us to find K. Let's see if we can do it. So half of the initial amount when T is 5730. So that is E, should be an E there, E to the negative k, which I'm trying to find, times this big number 5730. Okay, so does that make sense? Pretty similar to the last one. This one's just a little weird because this number is so big. But that's how carbon-14 dating works, or that's the half-life of carbon-14 is a lot of years. All right, but if we solve this algebraically, we'll do the same thing we did before. And then you're going to realize that that first step, you might not need it as you do these. Right? I like to always do the first step, but you might realize that that A naught's always going to cancel out. And then you end up here, and you take the natural log of both sides. All right, and that kind of eliminates. It just leaves you with negative 5730 times k is the natural log of 0.5, which we know is a negative number. Divide by negative 5730 to get k. Should be a very small number, right? Just because you know you're dividing by a very big number. So you should get a pretty small number. And when I do this, I get 0.03 zeros, 00012 if I round. All right. So now I have a function. Here's my function. It's whatever the initial amount is, e to the negative 0.00012t. That's the exponential decay model. All right. Now we can answer the question. Now, by the way, sometimes they ask for that, sometimes they don't. This one they don't. They just want to know how old it is. Okay. So how old is this model? Well, that's a t. And how am I going to find that? Well, what else do we have? We do know this initial, or we have this bit of information. Okay. So at 65%, so let's just plug it in and think about it. So at 65% is when, right, they found it, somehow they know 65%. So like when is that happening? How long until it reaches there? So that means if I plug that output in, the 65%, this will give me my answer, right? That's how long before it got here is the same question as how old is it when it's at 65%. Okay, so similar math what we just did, only instead of solving for k, since we already know k, since we found k, we're solving for t. All right, and the math is the same. This is an interesting problem because first you got to solve for k, then you got to solve for t. And you got to make sense of all these words, right? So this is pretty challenging. They're just asking you how old the artifact is. It's kind of a contrived problem because I think it'd be weird to, when I read this, I say, well, how do you know that it's 65% left if you don't know how old it is, right? It's kind of backwards. But anyway, we're just the mathematicians here. We're just asked to do the math, and that's what we can do here. Divide both sides by A naught. See if you can skip a couple steps. We always divide both sides by A naught, and then we take the natural log of that. And you know, you'd end up with the natural log of e to some power, which is just the power. And then, I mean, there's almost a formula. In some textbooks, there actually is a formula for this. You end up just dividing the natural log of that number by that number, right? And then that'll tell me how old this is. So before you plug this into your calculator, ask yourself, should it be greater than 5,730 years old or less than? The answer is it should be greater than this number, right? Because when half of it's left, oh, I take that back. It should be less than that number, right? It should be less than this number because there's more than half left. There's 65%. So it didn't get down to the amount at 5,730, right? There's still 65%. So the order I have my chart here is good. And when I plug that into my calculator, I say it is 3,560 years old, right? Which should make sense. Once it gets down to half of its original amount, it's 5,730. So it hasn't got down to half yet. So this seems about right.